Tonight, we are going to talk about a wall in the universe that nobody, no civilization, no technology, no amount of energy will ever break. A wall written into the fabric of the universe itself. The speed of light is 186,000 miles per second, and no object with mass, not a rocket, not a particle, not a spacecraft carrying the most advanced propulsion system our species could ever build, will ever reach it. Not because we haven't tried hard enough, not because the technology isn't there yet, but because the laws of physics have a hard rule here, and they don't bend for anyone. By the end of tonight, you are going to understand exactly why that wall exists, what happens when you push against it, and what that barrier means for every dream we've ever had about reaching the stars. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. In 1905, Albert Einstein was 26 years old. He wasn't a professor. He wasn't working at a prestigious research institution. He was a patent clerk in Bern, Switzerland, reviewing applications for electromagnetic devices during the day and thinking about physics at night. In that single year, he published 4 papers that together dismantled 3 centuries of assumptions about how the universe works. One of those papers introduced what we now call special relativity. The core insight sounds deceptively simple. The speed of light is the same for every observer, regardless of how fast they are moving. That's it. That's the premise. But the consequences of that one idea are so radical, so far-reaching, so deeply strange, that physicists are still working through them more than 100 years later. To understand why it matters, you have to first understand what physics said before Einstein. Isaac Newton published his laws of motion and his law of universal gravitation in 1687. His system was extraordinarily successful. It predicted the motion of planets with accuracy that no previous system had achieved. It explained why objects fall, why the moon orbits Earth, why comets return on schedule. For 218 years, Newtonian mechanics was the foundation of physics. It described a universe built on absolute time and absolute space. Time ticked at the same rate everywhere in the universe, from the core of a neutron star to the outer reaches of the cosmos. A second on Earth was a second in the Andromeda galaxy, a second anywhere and everywhere without exception. Space was a fixed, unchanging stage on which events played out. Objects moved through that stage, but the stage itself never moved, never bent, never changed. And velocities added together in the obvious way. If a ship moves at 50 miles per hour and fires a cannonball forward at 200 miles per hour relative to the ship, an observer standing on the dock sees the cannonball moving at 250 miles per hour. The speeds add. That's what every human being intuitively expects from centuries of lived experience in the everyday world. And for objects moving at the speeds we normally encounter, cars, bullets, aircraft, even rockets, the Newtonian picture works with extraordinary accuracy. The equations that sent Apollo astronauts to the moon and back were Newtonian equations. They were accurate enough to navigate to a moving target 250,000 miles away and land on it. The equations that guided the Voyager probes, launched in 1977 and still operating nearly 50 years later, are also primarily Newtonian. Voyager 1 is now nearly 16 billion miles from Earth, farther than any human-made object has ever traveled. It is moving at about 38,000 miles per hour relative to the Sun, That is fast by any standard of everyday experience. It is also about 0.0057% of the speed of light. At that speed, Voyager 1 would take roughly 73,000 years to reach the nearest star if it were aimed at it, which it is not. These are not failures of engineering. The Voyager probes are engineering triumphs designed to last decades, still transmitting data across billions of miles, having given us our first close looks at Jupiter, Saturn, Uranus, and Neptune. But they illustrate the scale of the problem with perfect clarity. The fastest sustained speed we have achieved with a spacecraft, over decades of travel, covers a fraction of a percent of light speed. The gap between that and what would be needed for any meaningful interstellar mission is not an incremental engineering problem. It is a difference in kind. But Einstein showed that the Newtonian picture breaks down at high speeds. Not because Newton made mathematical errors, not because the observations were incomplete, but because the universe operates on a fundamentally different principle than the one Newton assumed. Newton's framework was an approximation, an extraordinarily good approximation at low speeds, but an approximation nonetheless. The true picture is Einstein's. And in Einstein's picture, the universe has a speed limit that is absolute, universal, and inescapable. The principle that Einstein discovered is this: no matter how fast you are moving, no matter what direction you are traveling, no matter what your reference frame, a beam of light always passes you at exactly the same speed. 186,000 miles per second. Always. Without exception. This was not something Einstein guessed or inferred from intuition alone. It was preceded by decades of experimental results that Newtonian physics could not explain. In the 1880s, two American physicists, Albert Michelson and Edward Morley, performed one of the most precise experiments of their era. At the time, scientists believed that light, like sound, must travel through some medium. Sound travels through air, water, solid matter. The question was, what light traveled through? The proposed answer was the luminiferous ether, a substance filling all of space through which light waves propagated the way water waves propagate through the ocean. If the ether existed, Earth moving through it should produce a measurable effect on the speed of light measured in different directions. The way a swimmer moving against a current swims slower than one moving with it, Earth's motion through the ether should cause light traveling along Earth's direction of motion to measure slightly slower than light traveling perpendicular to that motion. Michelson and Morley built an exquisitely sensitive interferometer, a device that splits a light beam, sends the two halves along perpendicular paths, and then recombines them. Any difference in the speed of light in different directions would show up as a shift in the interference pattern. They measured, and they found nothing. No difference. Light moved at the same speed in every direction, regardless of Earth's motion. The experiment was performed many times, in different seasons, at different locations. The result was always the same: zero difference. The ether did not exist. Light did not need a medium, and its speed appeared to be independent of the motion of the source or the observer. This result bewildered physicists. For 2 decades, various explanations were proposed. The Dutch physicist Hendrik Lorentz, the same Lorentz whose name now belongs to the factor at the heart of special relativity, proposed that matter physically contracts in the direction of motion through the ether. He worked out the mathematics of this contraction and showed that it could, in principle, explain the Michelson-Morley result. If rulers shorten as they move through the ether, then measurements made with those rulers would always come out wrong in exactly the right way to make the ether undetectable. The Irish physicist George Fitzgerald had proposed the same idea independently around the same time. The Lorentz-Fitzgerald contraction, as it became known, was mathematically correct in a narrow sense. The numbers worked. But it was a patch, not an explanation. It said that matter contracts, but offered no physical reason why it should. It saved the ether by making the ether permanently unmeasurable, which is not the kind of explanation that satisfies a physicist for long. Henri Poincaré, the French mathematician and physicist, came perhaps closest of anyone to the full picture before Einstein. He recognized that the principle of relativity, the idea that the laws of physics should be the same in all inertial reference frames, was a deep symmetry of nature. He worked out much of the mathematics. He used the term relativity to describe the principle. But he did not fully let go of the ether. He could not quite bring himself to say that the ether was not merely undetectable, but genuinely unnecessary. That the mathematical framework he had helped build described a reality in which the ether simply did not exist. Einstein made that step. Einstein's solution was the most radical and the most complete. He accepted the experimental result at face value and asked what the universe must be like for it to be true. The answer was special relativity, and it required abandoning Newton's absolute time and absolute space entirely. Before getting to what special relativity actually says, it is worth pausing on something that tends to get skipped. The speed of light is 186,000 miles per second. But how do we actually know that? Measuring the speed of light is not straightforward. It travels so fast that for most of human history, people weren't even sure it had a finite speed at all. Aristotle believed light was instantaneous, that it traveled from place to place in zero time. Galileo disagreed, and in the early 1600s attempted to measure it by having two people on hilltops uncover lanterns at precisely timed moments. The experiment failed. The speed of light is so far beyond what human reaction times can resolve at distances of a few miles that the measurement was hopeless. The first real evidence that light has a finite speed came from astronomy. In 1676, the Danish astronomer Ole Rømer was tracking the orbital period of Io, one of Jupiter's moons. He noticed something odd. When Earth was moving toward Jupiter in its orbit, Io's eclipses happened slightly earlier than predicted. When Earth was moving away from Jupiter, they happened slightly later. Rømer correctly interpreted this as the effect of changing travel time for light across the varying distance between Earth and Jupiter. When Earth is closer to Jupiter, the light from Io's eclipses has less distance to travel, so we see them sooner. When Earth is farther away, we see them later. From the magnitude of this effect, Rømer estimated that light takes about 22 minutes to cross the diameter of Earth's orbit. The actual value is about 16 minutes and 40 seconds. Given the instruments and knowledge available in 1676, this was an extraordinary achievement. It was the first demonstration that light has a measurable, finite speed. Half a century later, the English astronomer James Bradley measured what is called the aberration of starlight, a tiny apparent shift in the positions of stars caused by Earth's motion around the Sun. A simple analogy: if you walk through rain that is falling straight down, it appears to hit you at an angle from the front. The faster you walk, the more the rain appears to come from ahead. Stars show the same effect due to Earth's orbital velocity. Bradley calculated a speed of light from the magnitude of this aberration that was closer to the actual value than Römer's estimate. On Earth, the first laboratory measurement came in 1849, when the French physicist Hippolyte Fizeau used a rapidly rotating toothed wheel to chop a light beam into pulses, sent those pulses to a mirror about 5 miles away, and measured how fast the wheel had to spin for returning pulses to pass through the gaps. From the wheel's rotation speed and the mirror's distance, he calculated the speed of light to within about 5% of the correct value. Later refinements by Léon Foucault and then by Albert Michelson, the same Michelson of the Michelson-Morley experiment, brought the measurement to within a fraction of a percent of the modern value. Michelson spent much of his career refining this measurement, conducting experiments with rotating mirrors and carefully measured baselines. His final measurement, completed shortly after his passing in 1931, gave a value within about 4 miles per second of the accepted figure. Today, the speed of light is not measured but defined. In 1983, the international scientific community redefined the meter in terms of the speed of light rather than the other way around. The speed of light in vacuum is now exactly 299,792,458 meters per second, or in round numbers, 186,282 miles per second. It is not a measured quantity anymore. It is a defined constant. The meter is defined as the distance light travels in a vacuum in 1/299 millionth of a second. The number is fixed by definition. What experiments measure now is everything else, distances, times, frequencies, in terms of that fixed constant. The speed of light has gone from being a mystery that baffled Aristotle to a quantity that took centuries to measure, to being the cornerstone of the entire international system of measurement. That is how central it is. If you are standing still on Earth and a photon flies past you, it moves at 186,000 miles per second relative to you. If you are on a spacecraft already moving at 90,000 miles per second, half the speed of light, and a photon flies past in the same direction you are traveling, you might expect it to move at only 96,000 miles per second relative to you, because you are already covering 90,000 miles per second of the gap between you and the photon. But that is not what happens. The photon still moves at 186,000 miles per second relative to you, the full speed, not reduced by your own motion at all. And if you are moving toward the photon, facing it head-on at half the speed of light, it still moves at 186,000 miles per second relative to you. Not 276,000. 186,000. The same number. Einstein's question was, how does the universe manage this? The answer is that space and time are not fixed. They flex. They adjust. They stretch and compress in exactly the right amounts to ensure that every observer, regardless of their velocity, measures light traveling at the same speed. Time runs slower for moving objects, a phenomenon called time dilation. Distances contract in the direction of motion, a phenomenon called length contraction. These are not illusions or measurement errors. They are physical realities, confirmed by precision experiments too numerous and too consistent to doubt. And, woven through all of it, is the consequence that makes the wall permanent. As an object with mass accelerates toward the speed of light, something happens to it. Something that no amount of engineering can overcome. the universe starts pushing back. And it never stops pushing back. It pushes back harder and harder, with increasing force as the speed increases. And the force required to push a little further becomes not just large but infinite before you ever reach the boundary. The mathematics of special relativity contains a quantity called the Lorentz factor. It's named after the Dutch physicist Hendrik Lorentz, who worked out some of the mathematical framework before Einstein provided the conceptual foundation. The Lorentz factor is a number that depends on velocity. At low speeds, it is essentially equal to 1. At high speeds, it grows. And as velocity approaches the speed of light, it grows without bound. The Lorentz factor describes exactly how much time dilation, length contraction, and effective mass increase an object experiences at any given velocity. It shows up in every relativistic equation. It is the mathematical signature of how the universe enforces its speed limit. At everyday speeds, even the fastest speeds humans have ever reached, the Lorentz factor is indistinguishable from 1. You would need to be moving at hundreds of thousands of miles per second for it to differ from 1 by even a fraction of a percent. At 1% of light speed, roughly 1,860 miles per second, the Lorentz factor is 1.00005, effectively 1. At 10% of light speed, it reaches about 1.005, still very close to 1. At 50% of light speed, it climbs to about 1.15. The object's effective inertia, its resistance to further acceleration, is now 15% higher than at rest. Getting to this speed already required an enormous investment of energy. Getting faster requires more energy still. At 90% of light speed, the Lorentz factor reaches about 2.3. The object's effective mass has more than doubled. Every bit of additional speed costs dramatically more than the previous bit. At 99% of light speed, the Lorentz factor is about 7. Pushing the object to 99.1% requires applying force against what now behaves as a 7 times heavier object. At 99.9%, the Lorentz factor exceeds 22. At 99.99%, it climbs to about 71. At 99.999%, it surpasses 200. At 99.9999%, it exceeds 700. The pattern is merciless and unrelenting. Every additional 9 you add to that string of 9s multiplies the effective mass by roughly a factor of 3. The energy required climbs correspondingly. And the speed approaches 186,000 miles per second, asymptotically always getting closer, always requiring more energy for each tiny additional fraction of a percent of light speed gained, but never, under any physical process, touching the boundary. To actually reach the speed of light, to touch that number exactly, would require the Lorentz factor to reach infinity. And infinite Lorentz factor means infinite effective mass. Infinite effective mass means infinite energy required to push the object. The universe does not contain infinite energy. Nothing with mass can ever reach the speed of light. This is not a technological barrier. It is not a problem that more powerful rockets will solve. It is not a challenge for the next generation of engineers. It is a mathematical consequence of how space-time works, confirmed by over a century of experiment, woven into the equations that describe every particle, every field, every force we have ever observed. The wall is real, and it is made of infinity. There is a related equation that most people have heard of, but rarely connect to this question. Einstein's most famous result is not special relativity itself, but a consequence of it. E equals mc squared. Energy equals mass times the speed of light squared. To understand why the speed of light appears in this equation, you have to appreciate what the speed of light squared actually is as a number. The speed of light is 186,000 miles per second. That is already an enormous number in everyday terms. When you square it, you get roughly 34,896,000,000 miles squared per second squared. That is the conversion factor between mass and energy. 1 kilogram of mass, fully converted to energy, releases energy equivalent to about 21.4 megatons of TNT. The largest nuclear weapon ever tested, the Soviet Tsar bomber, detonated in 1961, released energy equivalent to about 50 megatons of TNT. To produce that explosion, only about 2 kilograms of uranium and plutonium actually underwent fission. The rest of the weapon's mass, hundreds of kilograms of steel, lead, and other materials, contributed nothing to the explosion. 2 kilograms of matter, partially converting its mass to energy, released 50 megatons. And that partial conversion is the key word. Nuclear fission and fusion do not fully convert mass to energy. Only a tiny fraction of the available mass is converted. In a uranium fission bomb, about 0.1% of the fissile material's mass converts to energy. In a hydrogen bomb using fusion, the efficiency is higher, but still only a fraction of a percent. The sun converts mass to energy continuously through nuclear fusion in its core. Every second, the sun converts about 4 million metric tons of mass into energy through the fusion of hydrogen into helium. 4 million metric tons per second. That is what powers every beam of sunlight that has ever touched the surface of Earth. And even at that extraordinary rate, the sun has been burning for about 4.6 billion years and has used up less than 1/10 of its total hydrogen fuel. The number c squared, the speed of light squared, is so enormous that even tiny amounts of mass represent staggering reserves of energy. This is not incidental to the question of the light barrier. It is directly relevant. The reason you cannot accelerate a spacecraft to light speed is not that you don't have enough fuel in some practical engineering sense. It is that the total energy required is literally infinite, because the relativistic mass of the spacecraft grows without limit as it approaches the boundary. And E equals mc squared tells you the exchange rate. The closer you get to light speed, the more energy you need. And the more energy you add, the more it goes into effective mass rather than speed. The equation is not just a famous formula. It is a description of the same fundamental trap that the Lorentz factor describes. The wall is made of infinity, and infinity is not a practical engineering problem. It is a mathematical absolute. But the equation runs in both directions. It also tells you something about what happens when you try to accelerate an object to high speed. As you push energy into an object to make it go faster, that energy does not just become speed. At low velocities, nearly all of it becomes kinetic energy, the energy of motion. But as you approach the speed of light, something changes. The object cannot absorb more speed. The Lorentz factor is blocking that path. So, the energy goes somewhere else. It goes into the object's effective mass. The object gets heavier. Not in the sense that atoms are added to it. In the sense that its resistance to further acceleration grows, exactly as if its mass had increased. This is sometimes called relativistic mass, though modern physicists prefer to describe it in terms of momentum and energy rather than a changing mass value. The way to think about it is this. Every joule of energy you put into the object at high velocity has less and less effect on its speed, and more effect on its inertia. You are running harder and harder just to stay in place relative to the boundary. At low velocities, the energy-velocity relationship is familiar: 1/2 times mass times velocity squared, the classical kinetic energy formula. But as velocity approaches the speed of light, the correct relativistic formula diverges from that classical answer by larger and larger amounts. And as velocity approaches light speed exactly, the energy required does not just get large. It approaches infinity. The same boundary, approached from a different angle, gives the same answer. You cannot get there. The universe has written that conclusion into its most fundamental equations, and every path toward the boundary leads to the same wall. The experimental evidence for all of this is not abstract or indirect. It is some of the most robust and directly measured evidence in all of physics. The most direct comes from particle accelerators. At facilities like CERN in Switzerland, physicists accelerate subatomic particles to velocities very close to the speed of light. These machines pour enormous quantities of energy into individual particles and measure exactly what happens. And what happens is exactly what Einstein's equations predict. The Large Hadron Collider, which became operational in 2008, accelerates protons along a circular tunnel that is about 17 miles in circumference, buried roughly 300 feet beneath the French-Swiss border. The protons are accelerated to about 99.99999% of the speed of light. At that velocity, according to the Lorentz factor, each proton behaves as though it has an effective mass roughly 7,000 times higher than its rest mass. The rest mass of a proton is about 1.67 times 10 to the negative 27 kilograms. A proton, traveling at LHC speeds, has a kinetic energy of about 6.5 tera-electron-volts, a unit of energy used in particle physics. The total energy in both beams of the LHC, when they are running at full power, is equivalent to about 500 megajoules, roughly the kinetic energy of a high-speed train. All of that energy concentrated into beams of protons no wider than a human hair. And those protons are still not moving at the speed of light. They cannot. No matter how much energy you add to them, the Lorentz factor climbs, but never reaches infinity. The speed climbs, but never reaches the boundary. This is not a limitation of the LHC specifically. It is not a flaw in the accelerator's design. Every particle accelerator ever built, at every energy level, from the earliest machines of the 1940s to the largest facility in the world today, has produced exactly this result. The closer to light speed a particle gets, the more energy is required to push it further. The curve never flattens. The limit is never reached. And the curve follows the Lorentz factor equations with extraordinary precision. Not approximately. Exactly. The agreement between Einstein's predictions and the measured behavior of particles in accelerators has been verified to many decimal places over decades of experiments. It is among the most precisely tested relationships in all of science. Relativistic corrections are not always a matter of academic interest. In one case, they are a practical engineering requirement that millions of people depend on every day. Your phone's navigation system. The GPS network relies on a constellation of satellites orbiting Earth at altitudes of roughly 12,500 miles. Those satellites carry extremely precise atomic clocks. The entire system works by comparing the timing signals broadcast by multiple satellites simultaneously. Your device calculates its position by measuring tiny differences in when those signals arrive. The precision required is extraordinary. Errors of even a few billionths of a second translate into position errors of several feet. And here is the problem. The satellites are moving relative to you at about 8,700 miles per hour. Special relativity predicts that moving clocks run slow. At that speed, the satellite clocks lose about 7 microseconds per day relative to clocks on the ground. 7 millionths of a second per day. That sounds negligible. But accumulated over a single day, 7 microseconds of timing error translates to position errors of roughly 1.4 miles every day. Without correction, your GPS position would drift by over a mile per day, and after a few weeks, it would be useless. But there is a second effect, pulling in the opposite direction. General relativity, Einstein's theory of gravity, predicts that clocks run faster in weaker gravitational fields. The satellites are farther from Earth's center than clocks on the ground, so they sit in a slightly weaker gravitational field, and their clocks run fast by about 45 microseconds per day relative to ground clocks. The net effect of special and general relativity combined is that satellite clocks gain roughly 38 microseconds per day relative to ground-based clocks. 38 millionths of a second. The GPS system accounts for this by deliberately setting the satellite clocks to run slightly slow before launch, so that once they reach orbit and experience both relativistic effects, they tick at the correct rate. If the engineers had ignored relativity entirely, the system would fail within hours of operation. The relativistic corrections are not a theoretical nicety added for completeness. They are load-bearing parts of the engineering. Every navigation system on Earth that uses satellite positioning is a working demonstration that Einstein's equations are correct to the precision required for real-world technology. The speed of light is built into the infrastructure of the modern world. The evidence does not only come from machines we build. It also appears, naturally, written into events happening above our heads every second. Cosmic rays are high-energy particles, mostly protons and heavier atomic nuclei, that arrive at Earth continuously from sources across the galaxy and beyond. Some of the most energetic cosmic rays ever detected are moving at velocities so close to light speed that their Lorentz factors reach values in the tens of millions. We know this because of how they interact with Earth's atmosphere. When a very high-energy cosmic ray strikes an atom in the upper atmosphere, it creates a cascade of secondary particles, a phenomenon called an air shower. The pattern of particles in that shower, their energies, their angular distribution, their arrival times, all of these encode information about the original cosmic ray's energy. And the energy-velocity relationship, measured in those air showers, follows the relativistic equations exactly. Not a single cosmic ray has ever been detected traveling at or above the speed of light. Not one. In decades of cosmic ray observations, with detectors spread across hundreds of square miles, measuring energies spanning 15 orders of magnitude, the light barrier has held without exception. Then there are muons. Muons are subatomic particles produced when cosmic rays collide with atoms in the upper atmosphere at altitudes of about 9 to 12 miles. Muons are unstable. At rest, a muon decays into other particles after about 2.2 microseconds. 2.2 millionths of a second. Even traveling at the speed of light, which muons approach, but do not reach, a muon could only travel about 2,000 feet before decaying. But the atmosphere is about 30 miles thick. By the naive calculation, muons produced in the upper atmosphere should decay long before reaching the ground. We should not detect them at sea level. But we do. We detect them in enormous numbers. Muons rain down on every surface of Earth at a rate of about 1 per square centimeter per minute. The reason is time dilation. Muons, traveling at 98% of light speed, have a Lorentz factor of about 5. From our perspective, their internal clocks run 5 times slower than normal. What is 2.2 microseconds in the muon's rest frame stretches to about 11 microseconds from our frame. In 11 microseconds, at 98% of light speed, a muon travels about 2 miles. With additional considerations of length contraction from the muon's perspective, the 30-mile atmosphere appears contracted to about 6 miles from the muon's frame. They arrive at the ground. The muon count at sea level has been measured precisely. It matches the relativistic prediction exactly. If Newton was right, and time ran at the same rate for everything, the muon count would be drastically lower. The fact that muons reach sea level at the observed rate is a direct, daily confirmation that time dilation is real, that the Lorentz factor is real, and that the relativistic equations govern the universe at every scale we can measure. There is something else about the speed of light that deserves careful attention, because it often gets glossed over in popular discussions. It is not just the speed at which light happens to travel. It is the speed at which all massless particles travel. And more fundamentally, it is the speed of causality. Consider what causality means. An event happens, a star explodes, a planet forms, a signal is sent. That event can influence other events that come after it in time. But it cannot influence events that came before it. Cause precedes effect. Always. This is not a law we imposed on the universe. It is a property of the geometry of space-time. In the geometry that Einstein's equations describe a 4-dimensional manifold with what mathematicians call Lorentzian signature, every event has associated with it something called a light cone. The light cone divides space-time into regions. The future light cone contains all the events that the original event could possibly influence. The past light cone contains all the events that could possibly have influenced it. Outside the light cone, called the space-like region, are events that are causally disconnected from the original event. No signal, no influence, no information can pass between them. The boundary of the light cone, the surface itself, represents the path of a light beam. Only massless things travel on that surface. Everything with mass travels inside the light cone, always slower than light, always causally connected to its past in an unbroken chain. To exceed the speed of light would mean leaving your light cone. It would mean traveling into the space-like region. And the space-like region is not just hard to reach. It is categorically different from where you are. In the space-like region, the concepts of before and after become frame-dependent. Two observers, moving at different velocities, can genuinely disagree about which of two space-like separated events happened first. Neither observer is wrong. The events simply do not have a well-defined temporal order. They are outside each other's causal reach. If information or matter could travel faster than light could enter the space-like region, it would mean that the temporal order of events becomes negotiable. cause and effect lose their fixed relationship. From some reference frames, a faster-than-light message would arrive before it was sent. Not in some metaphorical or approximate sense. Literally, mathematically, in the equations, an event caused by that message would precede the sending of the message in some reference frames. This is the causality argument against faster-than-light travel, and it stands completely independently of the energy argument. Even if someone found a way to provide infinite energy, the causality violation would remain. The universe's insistence on a fixed direction of time, on cause always preceding effect, is not separable from the light barrier. They are the same constraint, expressed in different ways. The arrow of time is one of the deep mysteries in physics. Most of the fundamental laws of physics are symmetric. In time, they work equally well, run forward or backward. The equations of classical mechanics, electromagnetism, quantum mechanics, and general relativity do not distinguish between past and future at the microscopic level. A film of two billiard balls colliding, run in reverse, looks perfectly physical. And yet we all experience a clear, irreversible direction of time. Eggs break, but do not unbreak. Heat flows from hot objects to cold ones, not the other way. We remember the past, but not the future. The statistical mechanics explanation, rooted in thermodynamics, and the concept of entropy, explains why we experience time's arrow at the macroscopic scale, even though the microscopic laws are symmetric. But the causal structure of space-time adds another layer. The geometry of space-time enforces a distinction between the future light cone and the past light cone of every event. That distinction is not statistical. It is geometric. It is built into the shape of space-time itself, enforced by the same light barrier that prevents faster-than-light travel. The speed of light is not just a limit on how fast things can move. It is the guardian of temporal order. It is the thing that makes the word before meaningful. Remove it, allow faster-than-light signaling, and the concept of time's direction begins to dissolve in ways that make the universe as we know it impossible. The universe's insistence on 186,000 miles per second as an absolute ceiling is not arbitrary. It is load-bearing. It holds up the structure of causality that makes experience, memory, and the very idea of a narrative sequence of events possible at all. Two ideas come up regularly when people discuss faster-than-light travel, and both deserve a direct response. The first is tachyons. A tachyon is a hypothetical particle that would always travel faster than light. The idea was proposed in the 1960s, and it is mathematically interesting. In special relativity, the equations describe three categories of things. Objects with mass travel slower than light. Massless particles, like photons, travel at exactly light speed. And then, there is a third mathematical region, the region of speeds, faster than light, which the equations also describe, in the sense that they produce numbers there. Tachyons, in theory, would live in that third region. They would always move faster than light and would be unable to slow down to light speed, just as massive particles are unable to speed up to it. The boundary between the regions would be a barrier from both sides. The problem is that tachyons, if they existed, would violate causality in ways that cannot be resolved. A tachyon, carrying information from one place to another, would, in some reference frames, deliver that information before it was sent. Various theoretical patches have been proposed to avoid this, but none of them work cleanly. More practically, no tachyon has ever been detected. Not in particle accelerators, not in cosmic ray experiments, not in any observation of any kind. There is no experimental evidence that tachyons exist. And the theoretical problems with causality they create are severe enough that most physicists consider them a sign that the theory does not correspond to physical reality, rather than a genuine prediction to be taken seriously. The second idea is quantum entanglement. Quantum mechanics allows two particles to be entangled to share a quantum state such that measuring one particle instantaneously affects the state of the other, regardless of how far apart they are. This genuinely happens. It has been demonstrated in experiments at distances of hundreds of miles, and it genuinely appears instantaneous. The correlation shows up with no detectable delay. So, does entanglement allow faster-than-light communication? No. And the reason is subtle but absolute. When you measure an entangled particle, you get a random result. You cannot control what result you get. The other particle's state becomes correlated with yours the instant you measure, but the person at the other end also gets a random result. Neither of you can use this to send a message. To know that the results are correlated, you have to compare notes afterward, and that comparison must happen through normal channels, limited by the speed of light. The entanglement itself conveys no information. The correlations are only visible when the two sets of results are brought together and compared. And bringing them together requires a classical signal, subject to the same light speed limit as everything else. Physicists call this the no communication theorem, and it is not a loophole-prone result. It is a hard consequence of how quantum mechanics works. Entanglement is real, extraordinary, and deeply strange. But it does not allow information to travel faster than light. The universe is careful about this. Every mechanism that might seem to offer a shortcut turns out, on careful examination, to be blocked by the same fundamental constraint. Light travels at the speed of light, obviously. So the speed of light is achievable. But photons are not like particles with mass. Photons are massless. The Lorentz factor formula for a particle with mass doesn't apply to photons in the same way. When you put a zero in for the rest mass, the equations change their character entirely. A photon has no rest frame. There is no reference frame in which a photon is stationary. No matter how fast you are moving, a photon always passes you at 186,000 miles per second. From the moment a photon is created in the core of a star, in a light bulb filament, in a particle collision, it is already traveling at full light speed. It does not accelerate to that speed. It is created already there, and it has no choice but to remain there. Photons cannot slow down. They cannot stop. They cannot change their speed. They travel at exactly 186,000 miles per second for the entirety of their existence, from creation to absorption. The physics becomes even stranger when you try to think about the photon's own experience of its journey. Special relativity predicts that as an object's speed increases toward light speed, its experience time slows. At light speed for a massless particle, this time dilation becomes complete. From the photon's perspective, no time passes between emission and absorption. The star that emitted a photon and the telescope that absorbs it 8 billion years later from the photon's frame are the same moment. The photon does not experience duration. It does not experience travel. For the photon, its entire existence is a single timeless event. Think about what that means for a photon crossing the observable universe. A photon emitted in the core of a galaxy 13 billion light-years away traveling for 13 billion years by our measure, covering distances that would require our fastest spacecraft hundreds of trillions of years to cross from the photon's own frame of reference. That journey takes no time at all. Emission and absorption are the same moment. The photon does not wait. It does not travel in any experiential sense. It simply exists at both ends of its journey simultaneously, in the only frame that makes sense for a massless particle. This is one of the most alien aspects of the universe, revealed by special relativity. There is a category of existence, the existence of massless particles traveling at light speed, that is genuinely outside the reach of any experience we can have, or any technology we can build. We are made of matter. Our instruments are made of matter. Everything we interact with is made of matter, and matter cannot reach that boundary. This is not something we can explore. It is not somewhere we can go. A massive object approaching light speed would experience time slowing, but would never reach the limit where time stops entirely. The gap between 99.99% of light speed and light speed itself is infinite in terms of energy required. The photon's existence at that boundary is not a destination reachable by gradual approach. It is a categorically different kind of existence, belonging to a categorically different kind of entity. You are not a photon. Your atoms are not photons. No engineered system made of matter can become a photon. The boundary is not a fast road leading to a faster one. It is the edge of a conceptual cliff, and there is nothing on the other side for massive objects. There is one thing worth clarifying before moving on, because it comes up often and causes genuine confusion. The speed of light, 186,000 miles per second, is the speed of light in a vacuum, in empty space. Light does not always travel at that speed. When light passes through a medium glass, water, air, any transparent material, it slows down. In water, light travels at about 140,000 miles per second, roughly 75% of its vacuum speed. In glass, depending on the type, it travels at roughly 124,000 to 140,000 miles per second. In diamond, it slows to about 77,000 miles per second, less than half its vacuum speed. This slowing is not the same kind of limit as the vacuum speed. It is a physical interaction between the photons and the atoms of the medium. The photons themselves still travel at full light speed between interactions, but they are constantly being absorbed and re-emitted by atoms, which introduces delays. The effective speed through the material is the result of all those tiny delays accumulated. Now here is where it gets interesting. Because light slows down in a medium, it is actually possible for a massive particle to travel faster than light does in that medium. Not faster than light in a vacuum that remains impossible, but faster than the local speed of light in glass or water. When a charged particle does this, when it moves through a medium faster than light moves through that same medium, something remarkable happens. It produces a kind of electromagnetic shock wave. The same way a supersonic aircraft produces a sonic boom by outrunning its own sound waves, a particle outrunning light in a medium produces a cone of radiation. This is called Cherenkov radiation, named after the Soviet physicist Pavel Cherenkov, who first systematically studied it in the 1930s. It produces a characteristic blue glow, the eerie blue light you see in photographs of nuclear reactor cores submerged in water. That blue light is Cherenkov radiation, produced by high-energy electrons traveling through water faster than light travels through water. It is genuinely beautiful, and it is genuinely not a violation of the cosmic speed limit. The particles producing it are not exceeding 186,000 miles per second. They are exceeding the speed of light in water, which is a much lower bar, while still traveling well below the vacuum speed. The distinction matters because it is sometimes used to argue that faster-than-light travel is possible. It is not. Cherenkov radiation is a confirmation of special relativity, not an exception to it. The hard limit is 186,000 miles per second in vacuum. That limit has never been exceeded. Not by a particle, not by a signal, not by anything carrying information or energy. So, what does all of this mean for the dream of reaching the stars? The nearest star system beyond our own is Alpha Centauri, a triple star system about 4.24 light-years away. Light itself takes 4 years and 3 months to complete that journey. That is the absolute theoretical minimum travel time. No physical object with mass can do it faster. If we could somehow build a spacecraft that traveled at 90% of light speed, a velocity so extreme that no current or foreseeable near-term technology comes anywhere close, the journey to Alpha Centauri would take about 4.7 years from the perspective of observers left behind on Earth. From the crew's perspective, due to time dilation, it would feel closer to 2 years. And 90% of light speed is not remotely within reach of current engineering. The fastest human-made object ever, the Parker Solar Probe, at its closest approach to the Sun, reached about 430,000 miles per hour. That is an extraordinary achievement. It is also about 0.064% of the speed of light. The gap between the Parker Solar Probe's peak speed and 90% of light speed is not something you close with incremental engineering. The energy required to reach 90% of light speed with any meaningful payload is many orders of magnitude beyond what any plausible propulsion system can provide. Not because of lack of cleverness or engineering effort, because the energy requirements scale with the Lorentz factor, and the Lorentz factor at 90% of light speed is about 2.3, meaning the kinetic energy required is not just proportional to the square of the velocity, as in Newtonian mechanics, but scales in a way that makes the numbers astronomical even for modest fractions of light speed. For Sirius, the brightest star in the night sky at 8.6 light-years away, the minimum travel time is 8 years and 7 months at light speed. Any slower, and it stretches proportionally. For Vega, 25 light-years out, the minimum is 25 years. For the star Deneb, which anchors the tail of the constellation Cygnus and is one of the intrinsically brightest stars in our part of the galaxy, the minimum is roughly 2,400 light-years. For the center of the Milky Way, roughly 26,000 light-years. For Andromeda, 2.5 million light-years. These numbers do not shrink with engineering. They are set by physics. The light barrier does not just limit how fast you can move. It sets a permanent floor on how long each journey takes. And that floor, for most interesting destinations in the universe, is measured in years, decades, centuries, or millions of years. Some people hear this and ask what the most ambitious, real proposals for fast interstellar travel actually look like. Not fictional warp drives. Not theoretical shortcuts. The most serious, physics-grounded attempts to think about actually reaching another star. The most discussed real proposal is called Breakthrough Starshot. It was announced in 2016 by a group of scientists and funded by technology entrepreneur Yuri Milner. The concept involves launching not a crewed spacecraft, but an extremely small probe a light sail weighing just a few grams, roughly the mass of a paperclip. The idea is to accelerate that probe using an array of powerful ground-based lasers, focusing their combined output onto the sail and pushing it to a significant fraction of the speed of light. The target speed in the original proposal was 20% of the speed of light. At 20% of light speed, a probe could reach Alpha Centauri in about 20 years. That is genuinely fast, by any standard we have ever achieved. 20 years to the nearest star. Compared to the tens of thousands of years a conventional rocket would take at our current best speeds. But even this extraordinary concept, arguably the most technically aggressive real proposal ever seriously studied, faces enormous problems. The laser array required would need to produce roughly 100 gigawatts of power focused on the sail at launch. That is roughly 10% of the total electricity generating capacity of the United States, focused into a single beam. At 20% of light speed, the probe would pass through the Alpha Centauri system in a matter of hours with no ability to slow down. It would take 4 years for any signal from the probe to reach us, and any data it collected during those few hours of flyby would take another 4 years to travel back at light speed. The total mission time from launch to receiving the first data is over 20 years. For a paperclip-sized probe with no crew, no return journey, and no ability to stop at the destination. That is what serious, funded, peer-reviewed proposals for fast interstellar travel actually look like right now. Our current, best operational propulsion chemical rockets tops out at speeds measured in tens of miles per second. Ion drives, which use electric fields to accelerate charged particles as propellant, can achieve higher exhaust velocities but produce very low thrust, making them practical only for unmanned probes on long, slow journeys. Nuclear thermal propulsion, which uses a nuclear reactor to heat propellant, could theoretically reach speeds several times higher than chemical rockets, but still a tiny fraction of a percent of light speed. Nuclear pulse propulsion. The idea of detonating a series of nuclear explosions behind a spacecraft to propel it was seriously studied in the late 1950s and early 1960s, under a project called Orion. Theoretical top speeds for Orion-type designs were in the range of 3 to 5% of light speed, for the most aggressive designs using thermonuclear explosions. That is genuinely fast, and it would reduce travel time to Alpha Centauri to roughly 80 to 140 years. Still a multi-generational journey. Still constrained by the same physics. And still separated from the speed of light by a factor of 20 to 30, with the Lorentz factor barely beginning to bite at those speeds. Every realistic propulsion concept sits in the same vast gulf between what we can build and what the light barrier actually is. The gap is not measured in generations of engineering. It is measured in the fundamental physics of how much energy matter can carry, and how that energy translates into speed under the rules that space-time enforces. One more dimension to the problem of interstellar travel goes unnoticed until you actually do the numbers. Even if a crew somehow managed to reach another star, communication with home would be subject to the same light speed limit as everything else. Any signal sent back to Earth would travel at 186,000 miles per second, the fastest anything can travel. A crew at Alpha Centauri, 4.24 light-years away, could send a message home and wait for a reply. The message takes 4.24 years to reach Earth. Earth's reply takes another 4.24 years to come back. The round-trip communication time is about 8.5 years. Ask a question. Wait 8.5 years for the answer. Even within our own solar system, this delay is already a daily reality for mission controllers. Voyager 1, at nearly 16 billion miles out, is so distant that a radio signal traveling at the speed of light takes about 23.5 hours to reach it one way. Mission controllers sending a command to Voyager wait nearly a full day for the command to arrive, and then nearly another full day to receive confirmation. Close to 2 days for a round-trip communication with a probe that has not even left the Sun's gravitational influence in any final sense. At interstellar distances, this becomes completely unworkable for any kind of real-time coordination. A crew at the nearest star cannot ask mission control for advice and expect a useful answer within their operational timeframe. They are completely on their own from the moment they leave. This is not a solvable engineering problem. It is the light barrier expressing itself in a different dimension. You cannot send information faster than light any more than you can move matter faster than light. The isolation of an interstellar crew would be total and permanent. Not the temporary communication delays of the Apollo missions, 26 light seconds round trip to the moon, but years of silence between every exchange. And as a crew traveled farther, the delay would grow with every light year of distance. By the time they reached a star tens of light years away, a message sent at the moment of arrival would not reach Earth until decades after the crew left. The light barrier does not just slow the journey. It severs the connection to everything left behind. Now consider what happens to a crew that actually attempts to travel at a significant fraction of light speed. The physics of time dilation means that the crew ages more slowly than people left behind on Earth. At 99% of light speed, the Lorentz factor is 7. The crew ages 1 year for every 7 years that pass on Earth. A journey to a star 10 light years away and back at 99% of light speed takes just over 20 years from Earth's perspective. But the crew experiences less than 3 years of elapsed time. They return younger than their twin, who stayed home. This is the twin paradox, and it is not actually a paradox. It is a real physical asymmetry. The traveling twin accelerated and decelerated. The twin on Earth did not. The symmetry between them is broken, and the traveling twin genuinely ages less. This has been measured directly. Not with astronauts, but with particles in accelerators and with atomic clocks on aircraft. Unstable particles moving at near light speed in accelerators live much longer before decaying than the same particles at rest, by exactly the factor predicted by the Lorentz equation. Atomic clocks flown around the world on aircraft show slightly less elapsed time than identical clocks kept on the ground, by amounts that match relativistic predictions precisely. The effect is real. The math is right. But the time dilation, while remarkable, does not solve the practical problem of interstellar travel. A crew traveling at 99% of light speed to a star 10 light years away experiences about 1.4 years of travel time. That is manageable. But the star is still 10 light years away. The journey still takes just over 10 years from Earth's perspective. When they return, over 20 years have passed on Earth. Everyone they knew has aged. And crucially, they are still constrained to speeds below light speed. The time dilation makes the journey feel shorter for the crew. It does not make the distance smaller. The galaxy is still 100,000 light-years wide. To cross it, even at 99.99% of light speed, takes about 100,000 years from the perspective of the galaxy. The crew might experience a few hundred years of elapsed time. but the galaxy ages 100,000 years while they cross it. They arrive in a future so distant that the Earth they left might not exist anymore in any recognizable form. The light barrier traps not just the body, but the connection to home. Every journey to the stars is a one-way trip into the future. Another practical constraint on crewed interstellar travel does not get discussed often enough. Getting to even a modest fraction of light speed requires acceleration. And acceleration is something human bodies experience in a very direct physical way. 1 g of acceleration is what you feel sitting in a chair on Earth, the pull of gravity on your body. 1 g is comfortable indefinitely. It is what humans evolved to live in. 2 g is uncomfortable for extended periods. At 4 g, most people begin losing consciousness if sustained for more than a few seconds, because the heart struggles to pump blood to the brain against twice its normal challenge. Fighter pilots in high-performance aircraft routinely experience 8 or 9 g during tight turns, but only for fractions of a second. Sustained acceleration above about 5 g is life-threatening. Now consider what it takes to reach even 10% of the speed of light. 10% of light speed is about 18,600 miles per second. If you could sustain 1 g of continuous acceleration comfortable by human standards, it would take about 60 days to reach that speed. 1 g sustained for a year would bring you to about 77% of light speed, though the relativistic equations mean the actual speed gained per day decreases as you approach the boundary. This sounds encouraging. 1 g for a year sounds manageable. But that year of continuous 1 g acceleration requires an enormous amount of propellant. The fundamental problem is the rocket equation. To accelerate a spacecraft, you must throw mass out the back. The faster you want to go, the more mass you must throw out. And the propellant itself has mass, which means you need more propellant to accelerate the propellant, which means you need more propellant to accelerate that propellant, and so on in a vicious spiral. For a conventional rocket reaching a significant fraction of light speed, the ratio of initial mass at launch to final mass at the destination becomes astronomically large. A rocket using the best chemical propellants and needing to reach even 1% of light speed would require an initial mass dominated almost entirely by fuel, with the actual spacecraft being a tiny fraction of the whole. At 10% of light speed, the numbers become completely impractical with any propellant humans have ever used. Even with nuclear propulsion, the mass ratios required for relativistic speeds are beyond anything we have ever built. The only way to partially escape this trap is to leave the propellant behind, which is the logic behind the breakthrough Starshot laser sail concept. You do not carry your energy source. You beam it from a fixed location. But then you lose the ability to slow down. The sail that can be accelerated by a laser cannot be decelerated by one, at least not without a second laser array waiting at the destination, which would need to have been sent there in advance. Every solution creates a new problem. The physics is not cruel. It is simply consistent, and every approach to fast interstellar travel runs into the same underlying constraints, expressed in slightly different forms. There is a danger in near-light speed travel that the Lorentz equations alone do not capture. As a spacecraft accelerates towards significant fractions of light speed, the universe around it transforms. Radiation that was harmless at low speeds becomes dangerous. The interstellar medium that was negligible at low speeds becomes lethal. Space, which looks empty from our gentle orbital velocities, is not truly empty. It is filled with the cosmic microwave background, the faint thermal radiation left over from the early universe, filling all of space at a temperature of about 2.7 Kelvin, which is roughly minus 270.4 degrees Celsius, or minus 454.8 degrees Fahrenheit, just barely above absolute zero. At low speeds, this radiation is essentially invisible to any practical detection. Its photons are in the microwave part of the spectrum, low energy, harmless. But from the perspective of a spacecraft accelerating toward high fractions of light speed, those photons get blue-shifted. This is the relativistic Doppler effect, combined with aberration photons coming from the direction of motion pileup in both frequency and intensity. At 90% of light speed, microwave photons coming from the direction of travel are shifted to the near-infrared. Still not immediately dangerous, but the intensity in the forward direction has grown significantly. At 99% of light speed, those same photons shift into the optical and near-ultraviolet range. The ship is flying into increasingly intense radiation. At 99.9% of light speed, the cosmic microwave background photons, coming from ahead, have shifted into soft X-rays. The radiation dose to anything aboard would be significant. At higher fractions still, hard X-rays, and then gamma rays. The universe's background warmth, a temperature just barely above absolute zero that poses no threat at low speeds, has transformed into penetrating ionizing radiation, simply because of how fast the ship is moving through it. And that is just the background radiation. Interstellar space also contains particles. The average density in the diffuse interstellar medium between stars is about 1 hydrogen atom per cubic centimeter. At low speeds, encountering one of those atoms is a non-event. The collision energy is negligible. But at 99% of light speed, a single hydrogen atom strike delivers energy comparable to a particle beam in a research accelerator. At higher fractions of light speed, each hydrogen atom hit deposits energy that would blast through yards of the densest shielding material we know how to build. And while the average density is 1 atom per cubic centimeter, even at that sparse density, a spacecraft sweeping a cross-section of 10 square meters through 1 light-year of travel would encounter roughly 9.5 times 10 to the 22nd power atoms. 9, followed by 21 zeros, and then that 5. At near light speed, each of those collisions is a high-energy particle impact. The cumulative damage to a spacecraft structure, to electronics, to any biological crew would be catastrophic. No material we know of could serve as adequate shielding. No shielding thick enough to absorb these impacts at extreme fractions of light speed could be made light enough to be accelerated to those speeds in the first place. The faster you go, the more dangerous the universe ahead of you becomes. The light barrier attacks not just from behind, through energy requirements, but from the front, through the transformed radiation environment that near light velocity creates. There is something else that changes at near light speed that is rarely discussed but is striking to think about. The way the universe looks. From the perspective of a crew traveling at a significant fraction of light speed, the appearance of the sky around them would transform in ways that have no parallel in everyday experience. The first effect is called relativistic aberration. As you move forward through space, the light coming from stars ahead of you gets compressed into a smaller and smaller region directly in front. Stars that were spread across the entire sky appear to cluster toward your direction of travel. At 90% of light speed, Almost all the stars in the universe appear squeezed into a cone of about 26 degrees. Directly ahead, a circle, roughly the size of your outstretched fist, held at arm's length. The rest of the sky behind you would appear almost completely dark. The second effect is Doppler shifting of the light itself. Stars ahead of you are from your frame of reference, approaching you at near light speed. Their light is blue shifted dramatically. What was once visible light becomes ultraviolet, then X-rays. Stars that your eye could have seen in normal light become sources of invisible high-energy radiation. Meanwhile, the stars behind you are red-shifted into infrared and then microwave frequencies, becoming invisible to the naked eye. At high enough speeds, virtually none of the universe is visible in normal light. The stars ahead have shifted into wavelengths that would pass through your eyes without registering. The stars behind have shifted into wavelengths too long to see. The third effect is relativistic beaming. The blue shifted light from ahead is not just shifted, it is intensified. Photons arriving from the direction of travel are arriving more frequently and with more energy than they would at rest. The combined effect of aberration, Doppler shift, and beaming means that the visual experience of near light-speed travel would bear no resemblance to the starfield images from science fiction. There would be no streaking star lines. No gentle field of stars slowly growing brighter around you. Instead, a fierce, compressed, blue-shifted concentration of radiation directly ahead, shifting into increasingly deadly energy ranges as speed increases, against a darkening and eventually invisible sky behind. It would look less like flying through space and more like approaching a wall of light that simultaneously brightens and becomes lethal. The universe does not make near light speed travel comfortable to look at, any more than it makes it easy to achieve. There is something important about the universe's scale that adds another layer to all of this. The universe is expanding. Not expanding into anything. There is no edge it is expanding toward. Space itself is stretching, everywhere, in all directions, simultaneously. Galaxies are not flying apart through space like shrapnel from an explosion. The space between them is growing. This expansion was discovered in the 1920s by Edwin Hubble, who found that distant galaxies are moving away from us, and that the farther away they are, the faster they are receding. The relationship between distance and recession speed is described by the Hubble constant. At present, 2 points in the universe separated by roughly 3.26 million light-years recede from each other at about 46 miles per second due to the expansion of space alone. Now here is where the light barrier intersects with cosmic expansion in a striking way. If you go far enough, roughly 14 billion light-years in any direction, galaxies are receding from us at exactly the speed of light due to the expansion of space. Beyond that boundary, they are receding faster than light. Those galaxies are not violating special relativity. Nothing is moving through space faster than light. Space itself is expanding between us and them, and the rate of that expansion accumulated over tens of billions of light-years exceeds light speed. This boundary is called the Hubble horizon, or sometimes the cosmic light horizon. And it means that the observable universe is not the same as the total universe. There are regions of the universe from which no light will ever reach us, not because it hasn't had time yet, but because the expansion of space between us and those regions is carrying them away faster than light can cross the growing gap. Those regions are permanently beyond our reach, not because of the light barrier on our end, but because of expansion on the other end. The universe has more than one way of placing things permanently out of reach. The light barrier, governing how fast we can move, is one of them. The expansion of space removing distant regions from our observable universe forever is another. They are different mechanisms, rooted in different parts of Einstein's equations, but they point to the same conclusion. The universe is not organized for our convenience. It is vast, it is expanding, and it enforces hard limits on what any part of it can see, reach, or communicate with. Some proposals attempt to sidestep the light barrier entirely rather than push through it, not by accelerating an object faster, but by manipulating the geometry of space itself. The most discussed involves not moving a ship through space, but moving space around it. General relativity. Einstein's theory of gravity, published in 1915, describes spacetime as a dynamic structure that can curve and warp in response to mass and energy. In principle, the mathematics of general relativity allows for configurations of spacetime that could, in theory, transport a region of space from one place to another at any effective speed. The ship inside that region would not be moving faster than light relative to its local spacetime. It would be sitting still inside a bubble while the bubble itself moved. This is the idea behind the Alcubierre metric, proposed by theoretical physicist Miguel Alcubierre in 1994. Alcubierre was working at the University of Wales in Cardiff when he published a paper showing that Einstein's field equations permitted a solution where spacetime contracted in front of a ship and expanded behind it. The ship would ride the resulting wave like a surfer. From outside, the bubble could advance at any speed, including faster than light. From inside, the ship would sit in flat spacetime, experiencing no acceleration, no relativistic effects, no time dilation. When Alcubierre published the paper, the mathematics was correct. The metric he constructed was a valid solution to Einstein's field equations. That part is not in dispute. But building the thing would require something the universe appears not to contain in usable quantities. Negative energy. Matter with negative energy density. Ordinary matter, every atom of every object you have ever touched, has positive energy density. Mass curves spacetime inward. That inward curvature is what we call gravity. Negative energy density would curve spacetime outward. It would produce gravitational repulsion rather than attraction. No such material has ever been observed or produced in bulk. Quantum mechanics hints at contexts where the energy density of a region can be slightly below the energy density of ordinary vacuum. The Casimir effect is the most well-known example. Bring two conducting plates very close together in a vacuum, and they experience an attractive force. This happens because the allowed modes of quantum fluctuations between the plates are fewer than those outside, causing a tiny pressure difference. The energy density between the plates is technically slightly lower than the vacuum baseline. This is sometimes described as negative energy in a narrow technical sense. It is real. It has been measured many times. But the magnitudes involved are fantastically small. The Casimir effect between two plates, 1 micrometer apart, produces an energy density on the order of negative 1/10,000th of a joule per cubic meter. An Alcubierre drive would require negative energy densities enormously larger than this estimates. In the original formulation of the metric was so extreme as to be obviously impossible. Later work by researchers refining the proposal reduced the required amount dramatically by changing the shape of the bubble. But even the most optimistic revised estimates involve negative energy requirements that are far beyond anything the Casimir effect or any other known quantum process can produce. By orders of magnitude, likely many orders of magnitude, there is also a deeper problem. Most physicists believe that the energy conditions of general relativity, which are derived from what we know about how matter and energy behave in spacetime, cannot be violated on the scale required. The so-called weak energy condition and the dominant energy condition are not mathematically proven to hold universally, but they hold in every known physical scenario. And violations of the required magnitude, sustained over a macroscopic region, would likely trigger instabilities that would destroy any structure attempting to exploit them. The honest assessment of warp drives is not that they are mathematically forbidden. They are valid solutions to Einstein's equations on paper. The honest assessment is that building one would require matter and energy configurations that the universe appears not to permit, based on everything we know about quantum field theory and general relativity. Wormholes face the same obstacle from a different direction. A wormhole is a theoretical tunnel through space-time connecting two distant points. The mathematics of general relativity permits them. When Carl Schwarzschild solved Einstein's equations for a non-rotating, uncharged mass-producing what we now call the Schwarzschild black hole, the solution contained something unexpected. The interior of the black hole was connected, through the geometry of spacetime, to another region that could, in principle, be another location in the universe, or even another universe entirely. Einstein himself and his collaborator Nathan Rosen analyzed this structure in 1935. It became known as an Einstein-Rosen bridge. Later, physicist John Wheeler coined the term wormhole. The Einstein-Rosen bridge is not traversable. It forms and collapses so quickly in a time measured by the Schwarzschild radius divided by the speed of light that no traveler, no signal, no information of any kind can pass through before the throat pinches shut. The mathematics is unambiguous on this point. To make a wormhole traversable to hold the throat open long enough for anything to pass through requires threading it with exotic matter with negative energy density. The same exotic matter that warp drives need. And the problems are the same. We don't have it. We can't produce it in usable quantities. Whether it can exist in the required form at all is deeply uncertain. Even setting aside the exotic matter problem, traversable wormholes have stability issues rooted in quantum field theory. Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics conspire to prevent the formation of closed time-like curves, which wormholes with a time component would create. The conjecture is not proven, but there are strong arguments from quantum field theory that any traversable wormhole would be destroyed by quantum effects before it could be used. And there is the positioning problem. To use a wormhole as a shortcut, both ends need to be in the right places. One end at your starting point, the other at your destination. Getting the second end to your destination requires moving it there through normal space, subject to normal speed of light constraints. The wormhole cannot shorten that initial positioning journey. Only after the ends are in place can anything use it as a shortcut. And even then, causality constraints appear to limit what shortcuts are actually achievable, in ways that multiple physicists working on the problem have found difficult to circumvent. There is something important to understand about all these proposals. They share a common structure. They are not attempts to violate the speed of light, in the sense of moving an object through space-time faster than light. They are attempts to find loopholes in the geometry of space-time itself to reshape the stage rather than accelerate the actor. And the reason those loopholes seem to require exotic matter is not accidental. It is a reflection of the same underlying physics that makes the light barrier absolute for moving objects. The geometry of space-time and the behavior of matter in that geometry are not independent things. They are deeply entangled by Einstein's field equations. You cannot significantly reshape the geometry without the matter configuration required to source that geometry. And the matter configurations required to source traversable wormholes and warp bubbles appear to be configurations the universe does not allow. This connection is not fully understood at the deepest level. We do not yet have a complete theory of quantum gravity, a theory that unifies quantum mechanics with general relativity in a way that correctly describes all physical situations. This is not a minor gap. It is arguably the central unsolved problem in theoretical physics. General relativity. Our best theory of gravity and space-time describes the universe at large, scales with extraordinary precision. It predicts the behavior of black holes, the bending of light around massive objects, the expansion of the universe, the existence of gravitational waves. All of these predictions have been confirmed. Quantum mechanics, our best theory of matter and energy at small scales, is equally precise. It predicts the behavior of atoms, the properties of materials, the interactions of fundamental particles. It is the foundation of chemistry, of electronics, of every technology built from the manipulation of matter at the atomic scale. But the two theories are mathematically incompatible in regimes where both are needed simultaneously, near a black hole singularity. In the first instance, after the origin of the universe, in the throat of a theoretical wormhole. At the smallest possible scales of length and time, the Planck scale, where distances are roughly 10 to the negative 35 meters and time intervals are roughly 10 to the negative 43 seconds. At those scales, neither general relativity nor quantum mechanics alone gives the correct answer. A complete theory of quantum gravity, one that correctly handles all of these regimes, would replace both as limiting cases. The two leading candidates are string theory and loop quantum gravity, along with several other frameworks. String theory proposes that the fundamental objects in nature are not point particles, but one-dimensional strings, and that the different particles we observe correspond to different vibrational modes of those strings. It naturally incorporates gravity into a quantum framework and predicts the existence of extra spatial dimensions beyond the three we experience. Loop quantum gravity takes a different approach, quantizing space-time itself, treating it not as a smooth, continuous fabric, but as a discrete structure built from tiny quanta of space and time. Both frameworks make predictions in certain regimes. Neither has yet produced testable predictions that distinguish it cleanly from all alternatives using experiments we can currently perform. The energy scales at which quantum gravity effects become important are roughly 10 to the 19th power GeV, the Planck energy. The most powerful particle accelerator ever built, the Large Hadron Collider, operates at energies of about 6.5 TeV, 13 orders of magnitude below the Planck energy. We are 13 powers of 10 away from directly probing quantum gravity in a laboratory. That gap may never be bridgeable with any accelerator humans could build. This is the context for the uncertainty at the edges of our knowledge about wormholes and warp drives. The places where those proposals require exotic matter are the places where quantum gravity would operate. And in the absence of a complete quantum gravity theory, we cannot say with absolute mathematical certainty what is possible there. What we can say is this: every result from quantum field theory, the framework that combines quantum mechanics with special relativity, and which is the most precisely tested physical theory in history, supports the conclusion that the exotic matter configurations required for traversable wormholes and Alcubierre drives cannot exist. The energy conditions that appear to forbid them are not arbitrary. They follow from deep properties of how quantum fields behave in curved spacetime. Violating them on the scale required would likely introduce catastrophic instabilities. And nothing in the experimental record gives any hint that such violations are achievable. The honest position is uncertainty at the frontier, combined with very high confidence that within the domain where our current theories are well tested, which encompasses essentially all of practical physics, up to energies, many orders of magnitude beyond what any engineering has ever reached, the light barrier is absolute. There is one more layer to this story. Something that the energy arguments and the exotic matter arguments and the causality arguments all point toward but do not fully articulate. The speed of light is not just a number describing how fast photons travel. It is a fundamental constant of nature. It appears in the equations of electromagnetism, not as a speed that anything moves, but as a ratio between electric and magnetic fields. James Clerk Maxwell, working in the 1860s, unified the theories of electricity and magnetism into a single set of equations. Before Maxwell, electricity and magnetism were studied as separate phenomena. Electricity was what made amber attract feathers when you rubbed it, what flowed through wires, what accumulated in thunderclouds. Magnetism was what made compass needles point north, what made certain metals attract one another. The connection between them had been noticed experimentally moving. Electric charges produce magnetic fields, and changing magnetic fields produce electric currents. But no one had unified the two into a single coherent mathematical framework. Maxwell did that. His 4 equations, published in their complete form in 1865, described electric and magnetic fields in a unified way that captured every known electrical and magnetic phenomenon. And almost immediately, they predicted something nobody had expected. The equations allowed for solutions describing waves, self-sustaining oscillations of electric and magnetic fields that could propagate through space without any medium to carry them. A changing electric field creates a changing magnetic field. That changing magnetic field creates a changing electric field. And on, leapfrogging through space at a fixed speed, determined entirely by constants describing how strongly the vacuum responds to electric and magnetic fields. Maxwell calculated that speed. It came out to approximately 186,000 miles per second. He immediately recognized what this meant. Light is an electromagnetic wave. Not light as an analogy. Not light as a metaphor. Light, visible light. The thing you see with your eyes is a self-sustaining oscillation of electric and magnetic fields propagating through space at exactly the speed that Maxwell's equations predicted. He had not been trying to explain light. He had been trying to write down the rules of electricity and magnetism, and light fell out of the mathematics on its own. This was one of the great unifications in the history of science. What followed from Maxwell's equations was the recognition that visible light is just one small part of a much larger family. Radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays, gamma rays. All of these are electromagnetic radiation. All of them are the same phenomenon at different frequencies. All of them travel at exactly the same speed in vacuum, 186,000 miles per second. Not because they are all carrying the same kind of energy, not because they are all the same size, they span an enormous range of wavelengths, from the length of a building for radio waves down to a fraction of the size of an atomic nucleus for gamma rays. But they all travel at the same speed because they are all governed by the same four Maxwell equations, and those equations have one speed built into them. That speed is not something Maxwell put into his equations. It came out, and it matched measured values for the speed of light. This is why the speed of light shows up in E equals mc squared. This is why it shows up in the Lorentz factor. This is why it appears in the metric of space-time. It is not a coincidence that one constant appears in all these places. It is the same underlying fact about the geometry of the universe, expressed in different equations. The speed of light is the ratio of space to time in the fabric of reality. Change it, and you do not just change how fast light travels. You change the structure of space-time itself. You change how atoms are held together because electromagnetic forces are what hold electrons in their orbits. You change how stars burn. You change the energy levels of every chemical reaction. You change everything. The speed of light is not a parameter that happens to take a certain value. It is woven through the fabric of everything that exists. In the natural units that physicists use when working with fundamental theory, the speed of light is set to 1 not because it is small enough to ignore, but because it is the conversion factor between the space dimensions and the time dimension of space-time. Space and time are not just related by the constancy of light speed. They are made of the same stuff. They are different directions in a single four-dimensional structure. The speed of light is the conversion factor that tells you how much space equals how much time. 1 second of time is equivalent to 186,000 miles of space. That is the exchange rate written into the geometry of the universe. This is why the limit is absolute. It is not a rule imposed on a pre-existing stage. It is a property of the stage itself. Asking whether you could exceed the speed of light is, in a precise geometrical sense, asking whether you could rotate a time-like direction of space-time into a space-like one. The geometry does not allow it. The same way that three-dimensional space does not allow you to rotate the height dimension into the up direction while standing in place, the concepts simply don't map. The light barrier is not a traffic sign. It is the geometry of reality. Understanding all of this changes something about how you look at the night sky. Those stars you see on a clear night, the ones that have drawn the attention of our species since before recorded history, are not just far away in the ordinary sense. They are separated from us by distances the universe has made structurally unreachable at any speed we can achieve. The nearest star system, Alpha Centauri, sits 4.24 light-years away. Even light, the fastest thing the universe permits, takes 4 years and 3 months to bridge that gap. Every star beyond that is farther still. Some of the stars you can see with the naked eye are dozens, hundreds, or thousands of light-years away. The light arriving at your eye tonight from some of those stars left long before you were born, long before anyone you know was born. In a few cases, long before anyone we call an ancestor was alive. You are not seeing those stars as they are. You are seeing them as they were, frozen in the light that left them years or centuries or millennia ago. The universe is an archive of its own past, and you are reading it. When you look at the Andromeda Galaxy on a clear dark night, a faint smudge visible to the naked eye under the right conditions, you are seeing light that left it 2.5 million years ago. That light has been traveling since long before our species existed. When it began its journey, there were no humans on Earth. When you look at more distant objects, the time depths become staggering. The most distant galaxies visible to the Hubble Space Telescope and its successors are so far away that the light reaching us left them when the universe was less than 1 billion years old, when the first generations of stars were just igniting, when the large-scale structure of galaxies was still forming from clouds of gas. We are not just looking at distant places. We are looking at different times. The night sky is a time machine. Every direction you look is a different depth into the past. And the light speed limit is what makes this possible in the first place. Because light takes time to travel, the universe has a natural record-keeping system. The further back in time you want to look, the further away in space you must look. The two are the same thing, connected by the speed of light. This connection between distance in space and time in the past is so fundamental that astronomers describe distances in terms of light travel time. A galaxy 10 billion light-years away is also a galaxy, seen as it was 10 billion years ago. The same law that prevents us from traveling fast enough to reach those galaxies is the law that makes them historical records of the early universe. The light barrier is simultaneously the thing that keeps us here and the thing that gives us a window onto the entire history of the cosmos. We cannot go there, but we can see there. And what we can see extends across 13.8 billion years of cosmic history, encoded in the light that arrives at our telescopes every night. That is not a consolation prize. That is an extraordinary gift from the same physics that draws the line we cannot cross. But reaching those stars, traveling to them, not just observing them, means crossing the distances that those light travel times represent. And no spacecraft, no engine, no propulsion concept, no theoretical shortcut that physics permits can eliminate the minimum time that those distances impose. This is not a problem science has not yet solved. It is a property of the universe that science has precisely and quantitatively described. The answer to the question of whether we can reach the speed of light is not yet. It is, the geometry of space-time does not allow it, and we have confirmed this to extraordinary precision in every experiment ever designed to test it. None of this makes the cosmos smaller in the ways that matter most. The questions we can ask about it are as vast as they have ever been. The observations we can make from here and from robotic missions extending our reach across the solar system and beyond reveal a universe of staggering richness and complexity. The physics that forbids us from reaching light speed also predicts phenomena of extraordinary beauty, time dilation, gravitational waves, the curvature of space-time around massive objects, the existence of black holes, the expansion of the universe itself. All of these are fruits of the same equations that draw the boundary we cannot cross. The light barrier is not a disappointment. It is a description. It tells us, with precision and honesty, what the universe is. And there is something clarifying about that honesty. Consider what it actually means that we know this at all. We are biological creatures. We evolved on one planet, orbiting one star, in one galaxy. Our brains developed over millions of years to solve problems at the scale of the everyday world, to track prey, to recognize faces, to navigate terrain, to communicate with other members of our species. None of the challenges our ancestors faced required any understanding of what happens to time at high velocities, or why space and time are the same thing measured in different directions, or what the geometry of space-time looks like near a singularity. Evolution did not equip us for these questions. There is no survival advantage in understanding the Lorentz factor. There is no reproductive benefit to deriving Maxwell's equations. And yet, we did it anyway. Starting from the same basic cognitive equipment that our ancestors used to hunt and gather and build fires, we developed mathematics and then science. And then the extraordinary theoretical and experimental apparatus that produced special relativity, general relativity, quantum mechanics, and everything that flows from them. We found that the universe is not organized at human scales. Its deepest structures operate at scales far smaller than atoms and distances far larger than galaxies, at speeds that no human being has ever directly experienced, under conditions of energy and density that would instantly destroy anything biological. And yet, we reached into those scales with our instruments and our mathematics and pulled out the rules. We measured the speed of light to better than 1 part in a billion. We accelerated particles to within 1/100000% of light speed and watched them behave exactly as Einstein's equations said they would. We detected gravitational waves, ripples in space-time itself, produced by 2 black holes merging over 1 billion light-years away, using instruments sensitive enough to detect a change in Preit, distance smaller than 1,000th the diameter of a proton. We observed the cosmic microwave background, the afterglow of the early universe, and read, in its temperature fluctuations, the seeds of every galaxy that has ever formed. We did all of this without leaving the solar system, without traveling even to the nearest star, without ever exceeding a tiny fraction of a percent of the speed of light. The light barrier closes off the physical universe to us in one specific way. It prevents us from going there in any meaningful time frame, but it does not prevent us from knowing it. The same physics that limits our travel gives us telescopes that can see 13.8 billion light-years into space and time. The same equations that enforce the speed limit reveal the structure of black holes, the history of the cosmos, the nature of matter and energy at their most fundamental level. We are on a small planet, orbiting one star, among hundreds of billions in a galaxy that is itself one of hundreds of billions of galaxies. The distances between all of these things are vast, beyond easy comprehension, and the laws of physics set absolute limits on how quickly any of it can be reached. That is the actual shape of our situation, not a pessimistic interpretation of it, not a technological constraint that the next century of engineering will dissolve, the actual geometry of where we are. And within that geometry, from this one small vantage point, we have mapped the history of the universe. We have worked out the rules that govern everything from quarks to galaxy clusters. We have found the speed limit of reality itself and understood precisely why it exists. A species that can do that knows the universe well enough to measure its speed limit, describe the equations that enforce it, and explain precisely why it cannot be crossed, is a species with genuine insight into the nature of reality. Whatever we do with that knowledge, however we direct our curiosity and our engineering in the centuries ahead, it should be informed by what we actually know, rather than by what we wish were true. The speed of light is 186,000 miles per second. It is the speed of causality, the exchange rate between space and time, the boundary of every light cone in the universe. It has been tested by every precision instrument ever pointed at the question, confirmed in particle accelerators and cosmic ray detectors and atomic clocks and GPS corrections and muon arrival rates and the behavior of every electromagnetic wave ever measured. And nothing with mass will ever reach it. Not because the dream of the stars is wrong, but because the universe has a specific and measurable geometry, and that geometry draws a line that mass cannot cross. That is the answer. And perhaps the most extraordinary thing about all of it is that we are the kind of creature that can figure it out. That we can stand on a small planet, look up at a sky full of unreachable fire, and work out from first principles exactly why it will remain unreachable, not forever, not if technology improves, but in a far more fundamental and permanent sense. The universe does not accommodate infinite energy. The geometry of space-time does not allow massive objects to reach the surface of the light cone. The wall is real, and understanding exactly what it is made of and exactly why it stands is one of the great achievements of human science. Good night.